Thank you. Hello, everyone. Good afternoon. Welcome to the Tech.eu Summit. I'm Duygu Clark. I'm investing in early-stage tech startups based out of San Francisco. And today, we have the privilege of exploring a topic of utmost importance. In our increasingly interconnected world, the convergence of artificial intelligence, cybersecurity, and quantum computing represents both challenges and opportunities. From safeguarding the sensitive data to fortifying critical infrastructure, the stakes have never been higher as we navigate the complex intersection of these technologies. But lucky us, we have two experts who are the best of the best in their field. So I'm honored to introduce them, who bring a wealth of expertise and insights to our discussion. Dr. Ken Urquhart, I practiced the last name, but
Thank you.
A global VP of 5G Edge Satellite at Zscaler, whose expertise lies at the forefront of cybersecurity innovation. And Mr. Steve Brierley, founder and CEO of Riverlane, a visionary leader in quantum computing. So thank you so much for being with us today.
Thank you.
I want to start with Dr. Ken.
Thank you.
Since I cannot pronounce the last name, I'm going to go with Dr. Ken. AI is increasingly being used to detect and respond to cyber threats in real time. Mm-hmm. In your experience, what are the limitations of artificial intelligence in cybersecurity, and how can quantum computing potentially can address those challenges?
Interesting question with an uncertain answer. That's like my one physics joke I can tell today. AI, the way we're applying it, there are algorithms that are interpretable. We know how they behave. They're rather simple. And the good news is for a lot of AI in cybersecurity, you need the older machine learning algorithms are used extensively in their known results, very useful. But when you get to the current generation of AI with neural networks, with convolutional systems, large language models, you get additional problems, which is your answers are statistical in nature, meaning it's sort of like this. It's probably like that. We have these issues of hallucination you've heard, which is just a nice word of saying the AI is making things up that may not be true. And you have something called drift, which means the answers can become less accurate as time goes on. Even if you ask the same question twice in a row and you have a space of hours or days between them, you can get less accurate answers. So it's helpful, but you need to be thoughtful how you apply it. Quantum computing is a way of doing a lot of statistical related operations faster, really fast. Like taking something that can take the age of the universe in classical computing and shrink it down into hours or days. Great. So there's a lot of research going on that says, how do I take quantum mechanical computers and algorithms, which are kind of different from what you do with classical computing today, and adapt those statistical rapid processors to the fundamentally statistical nature of machine learning algorithms and neural networks. Great promise. Really indeterminate when that's going to happen. I hear, oh, next year, oh, 5 years, maybe 40 years. We don't know yet, even though my friend Steve is doing fundamental work that can make quantum computers viable faster.
Yeah.
So he's the real expert here on stage.
Yeah, actually, my next question is for Steve. So Andrea of NATO Innovation Fund just told us in the previous session that the quantum computing will be the most important topic in the short, mid, and the long run. And your research showed us that actually we are not that far away from that reality. So I really want to ask you, how soon do you think quantum computers will be capable of breaking widely used encryption standards, and what steps should organizations take now to prepare to this situation?
Yeah, great. So I think the good news is it's not tomorrow. So just to be clear, the quantum computers that people are building today, they are extremely error-prone. So they can perform about 100, perhaps 1,000 operations before the fragile nature of the building blocks of the quantum computer overwhelm the computation, and the whole computer actually grinds to a halt. Now, to break, to break RSA at a kind of cryptographically relevant scale, we need to get to on the order of 1 trillion operations. So that's a really big gap. Now that gap's solved by, or addressed by, solving what's called quantum error correction. So this is a layer that sits on top of the physical qubits and corrects errors in real time. Yeah. OK, I'm going to switch to this one. Great. So I was just explaining that quantum error correction is this key technology in quantum computing. It sits on top of the physical qubits and corrects errors as the computation is running. And this is how we're going to get to large-scale quantum computers. I think what's really exciting in quantum computing right now is that the physical qubits, so the underlying building blocks, these are now essentially got to the stage where they're good enough to start adding error correction on top. So if your physical qubits are extremely noisy, if they're just absolutely terrible, then adding error correction just makes things worse. And you get to this tipping point, it's called the QEC threshold, which is essentially means that when you add error correction, things start to get better. And so 2023, 24 was the year when we crossed that threshold in a number of different qubit modalities. And I think this explains why all of a sudden quantum error correction is top of the agenda, why people are getting extremely excited about the technology, because I think we now have a very clear path to building the first error-corrected quantum computers. Now, these won't be the trillion operations. They'll perhaps do about 1 million operations. But that's way more than we can currently do, and it goes beyond the capability of something we can simulate. So 1 million quantum operations couldn't be simulated on any classical computer. The equivalent compute power would be on the order of 1 billion trillion GPUs. So just an enormous amount of capability. It's still limited. It's still going to be the kind of early demonstrations. And many people in the industry are super excited about this moment in time when we break through this barrier. So I think that's coming in the next 2 to 3 years, essentially because the basic science has been solved to get to that point. But to be clear, then we need another 2 or 3 significant steps forward to get to this kind of cryptographically relevant scale of computing.
But this is all exciting and also scary at the same time, because as we advance in AI and quantum computing, new ethical and security challenges emerge. So, Dr. Ken, how can organizations balance innovation with ethical considerations?
That's an interesting, simple question to ask, and a multifaceted answer, which I'm not sure I can even adequately begin to address. But it's knowing the limitations of what you're applying. You don't, like, for example, I went to ChatGPT and I said, write me a biography. It said I worked for the United Nations at some point. For the record, I've never worked for the United Nations. That's an example of hallucination. I know of others who've asked it to write a bio, and it's come up with things saying they've committed some rather heinous crimes. So are you going to use ChatGPT in its current form to write yourself a bio? I would advise against it unless you want to do a lot of editing. Asking it to write certifications, asking it to write about scientific topics are all really interesting. It's like a fascinating look into the future, but it won't be accurate. We'll get there eventually, I think, but relying too much on these technologies to make decisions affecting citizens, affecting businesses, affecting human lives is not something it's ready for. And I think we all need to be aware of that. We're on a journey with artificial intelligence. It does not think at the present time. It is a collection of statistical outcomes, putting together words that happen to be close enough together in this body of knowledge you've exposed it to. It can do really interesting things. It can also do very horrible things that can ruin lives, and we need to be cognizant of that.
So you said we are on the journey in AI. We are also on the journey in quantum computing. And Steve, I know that you work with leading industry partners from climate science to advanced material to identify the specific areas that quantum computing can advance the human progress. So can you share some specific examples of how quantum computing is being utilized in these sectors?
Yeah, absolutely. I think the foundational capability of a quantum computer is the ability to simulate how proteins move, how atoms interact, and how electrons move across a material. So this is because the equations of motion of these systems are quantum mechanics. So we've known these equations for 100 years, and the quantum computer allows us to the first time to solve the equations. And so this means that in applications like the search for a new catalyst to reduce the energy consumption in an industrial process, or the search for a better battery material, we can replace the time-consuming lab experiments, the tests and the work that takes many, many years with a simulation on a computer. So the quantum computer can generate new data for industries that are fundamentally working on properties of systems that are extremely small. I think the clue is really in those industries that are still doing discovery. Right? We still do drug discovery, we still discover new materials, we discover new catalysts. But in other industries, like in aerospace, we have the equations of motion, and we have the computers that can solve those equations. And so in those industries, products are designed. They're designed on computers. And so the potential of quantum is to transform many industries into an age of design.
Awesome.
Now, just to amplify that, if I could, am I allowed to amplify on that?
Please.
Richard Feynman, the Nobel Prize winner, wrote a paper in the 1980s that initiated the thinking about a quantum computer. Why did he write it? Did he write it to say, oh, we can factor two large prime numbers and break encryption? No. He wrote it because at the time, computers were such that you couldn't simulate even the most simplest atomic systems. So you couldn't understand in depth how they interact and how you might build something of value based off of the simulation. So he proposed a computer that was essentially quantum in nature to have the kind of capability of solving these complex systems that we didn't have enough compute power in the entire world to solve at the time, even the simplest systems. A system with 16 atoms was insoluble. A system with 8 atoms, there wasn't enough compute power. So we're looking at solving essentially quantum mechanical problems with a quantum computer. Will everyone need to become a quantum programmer, a quantum computing programmer? Probably not. Is it going to solve every algorithm? Probably not. There's certain kinds of problems that can advance civilization that quantum computers will solve, but not everybody's going to end up using them. There's a lot of problems we can solve today. You'll never use a quantum computer to run payroll, for example, unless it's sort of a stunt to show that it can do it in a millionth of a second instead of taking 2 seconds. Okay, I'm
Use
done.
it for better
Sorry.
purpose. No, it was great. Now I have a question for both of you. With the complex interplay of AI, cybersecurity, and quantum computing, collaboration among academia, industry, and government entities becomes crucial. So how can we foster greater collaboration and standardization efforts to make sure we have robust solutions to safeguard our digital future? Steve, let's start with you.
Yes, I agree. I think collaboration is absolutely essential. I think this is a technology and space where there's no way we want to come second. Right? As a democratic society in the West, I think this is a technology that it is crucial to win. And so we effectively need some kind of Manhattan-scale project to build the biggest quantum computers in the world. Now, that could happen by a single organization with a single leader implementing it, but actually I think the best way to do this is through collaboration across industry, across academia, across national labs, where we're seeing a huge amount of innovation right now in companies pursuing different qubit types, for example, or different parts of the technology stack. And this has had a huge, this has been working extremely effectively. I mean, we basically have a kind of Moore's law already in quantum computing. For the past 15 years, you've seen essentially a doubling in capability every 12 to 18 months across multiple approaches. So this race is super hot right now. And I think it's essential that these efforts are effectively coordinated because the potential for good and for bad is so big.
Awesome. Dr. Ken, what do you think about how can we foster greater collaboration?
I think it's a matter of commercial entities are the engine of innovation and monetization. Universities create knowledge, and that knowledge begins this journey to commercialization through a company. Like you started out, you had research, had an idea, and found people who would back it and now are taking it to market. That's a classic way of doing it. Government is there to put a regulatory environment and possibly a funding and early stage funding environment to spark these innovations, to make these possible. But in the end, the government doesn't run a business of quantum computing. That will come out of industry. And so the machinery is there. We just typically have to have the will to engage it and make it run. You know, it sounds incredibly simple, but in truth, it's incredibly hard because all of this depends on people, meaning we have to work together, understand each other, know how to talk to each other. And sometimes that's the hardest part. It's got nothing to do with the technology and everything to do with us.
Yeah.
And as far as quantum computing, I know I just want to cast everyone's mind to what it really is going to happen. Is it going to be a bunch of gold-plated chandeliers dipped in liquid helium? That's an early stage. Eventually, we're looking at photonic quantum computers where you could have a quantum computer running an AI capable of solving most of the problems on this planet, capable of telling you how to build a warp drive and go to the stars, that might look like a very complicated crystal you could hold in your hand. And what kind of world would you have when everyone had something capable of doing that and coordinating the world? You know, that's the kind of future that people who think about these things reach for. And they're the kind of ideas that drive society forward, hopefully in a good way. Hopefully it doesn't race so far ahead that it outstrips our ability to understand the ramifications to our world. So I'm going to end on that big idea.
I was really interested in both of your answers because you worked for IBM, Microsoft, like all the big names, and you're coming from academia as well. And Steve, you worked at, you did a lot of research actually. Your research is kind of revolutionary in your field, but now you're in the startup world. So that's why I think your points were so important. So thank you for your answers. And I know we are running out of time, but I want to ask one last question before we wrap up the panel. So Steve, in your opinion, what is one thing that people is getting wrong about quantum computing?
That it's just a faster computer. It's more subtle than that, and actually more interesting. So quantum computers are a massive step forward for some problems, and as you said, Ken, will also be completely irrelevant for other problems. And so the class of problems to have in mind are things that involve the very small, the molecules and the proteins of the world.
Okay, Dr. Ken, last question. Same question for you, but I'm asking for the cybersecurity. What is one thing that people are getting wrong in cybersecurity?
In terms of AI and quantum computing, or just in cybersecurity?
Just in cybersecurity.
You wait too long to adopt new technology. Quantum computing will break most encryption at some point. Nation-state actors are stealing your data today and holding on to it to decrypt in the future. A quantum breakthrough could come in as few as a few years. There was a time we had a way of fingerprinting documents with an algorithm that turned out to be breakable so people could modify a document and you would think it was the original. And people took way too many years to move away from that because they'd made an investment and didn't want to change. When quantum computing happens, when the Shor's algorithm breaks encryption, there's going to be companies that will say, do I really have to change? And we are going to be, I'll just tell you right now, we'll be caught flat-footed. Everybody go, I thought it'd take longer. And we're going to all act surprised. Well, I'm here to tell you, it's going to rock your world in a very bad way. And you're not going to be ready for it because that, as I said earlier, is human nature. And we'll all, say, oh, this is terrible. You're being warned with, businesses, you're being warned with lots of time. And it's going to catch a lot of you seemingly unaware. So there, I shall be Cassandra today, and I shall tell you this is going to happen. And many of you will say, I'll wait a while. Please don't.
Great, thank you so much. So as Dr. Ken and Steve said, we are on a journey in terms of cybersecurity, AI, quantum computing. But as Dr. Ken said, don't sleep on it. So please follow Dr. Ken
Your government
and Steve.
has advice for you today. It's there to apply. It's freely available. Please read up on it. Please heed the warnings.
Awesome. Thank you so much, Steve and Dr. Ken.
Thank you for having us.
See ya.